The RT transpiler transpiles RT, very high-level language, to Python. This is done as a pipeline containing 5 steps. I show the pipeline here using the draw.io editor. The first step is inhaling, turning the input source code from RT into some internal form I will describe later. We do a syntax check, then we do a semantics check, then we do the actual transpilation from RT to Python, and then we change the internal form back to legal Python and output it here. And if there's errors anywhere along the way, we get an error message on this output port. As you can see, each box has an error output of its own. The inhale step is broken down into 2 pieces. First, it gets a file name, reads it in, and sends all the characters to this next box. This next box calls a local shell file NDSL. The $sign in the name means to spawn a local shell, visual shell basically. This DSL takes a grammar file and a rewrite file. The grammar for the internalizer is fairly simple. It has several rules: text char, string char, comment char, word char, ID. This is a leftover historically, and new line. Let's just look at one of these rules, string char. It says it looks for an open Unicode quote. Note that the quote is different than the quotes we usually use in existing languages. There's a begin quote and an end quote. They're different. When this pattern is matched, the parser calls char underscore string in the rewrite rules down here. What this basically says is match an open quote, match 0 or more string chars, and then match a closing quote. And the string chars are defined down here. We do it recursively, which normally can't be done in most existing languages. Because we have separate open and close quotes, we're using parsing expression grammars, pegs. Means we can embed strings within strings. And basically it says if it finds one of these, then it calls a recursive rule, and otherwise don't match either of these quotes, match anything else, and call string char other. Now let's look at the rewrite. This is in internalize.rewrite. There's a small DSL that helps rewriting strings to strings. And again, let's just look at the one rule that gets called when strings are matched. When a string is matched, the parser calls this rule and passes in 3 parameters: the left quote, the right quote, and a tree of 0 or more characters. The rewrite itself is enclosed in these backticks, a backtick and a different kind of backtick. And it emits a open quote, close quote, and then calls an internal function in the support function library called encodeWS, and it passes the value, the interpolation of the C's from here into here to encodeWS, and the result of that is stuffed in here, and then the whole thing, the whole rewritten string is returned as the value of this rule. If we follow this rule down into the support file, what we're doing is trying to convert all white spaces into some sort of printables that won't be picked up as spaces in subsequent passes that use Ohm's syntactic rules. Syntactic rules make grammars easier to write, but they do have the catch that in languages that don't use a lot of commas or semicolons to separate things, sometimes adjacent multiple identifiers can look as single identifiers. And if we look in here, encodeWS simply calls encode URI component, and then encode quotes. It does a little bit more replacement than what's available in the stock encode URI component. Likewise, if we look at what happens with a new line, we call get line inc. So every time we see an incoming new line, we just note what input source line number it came in on. We save it into a global variable here. We increment it, and then we return it as a text numeric. That gets stuffed in here, in comments, with a new line after it. Most languages don't need this extra new line, but Python only supports new line comments. And we have to make sure there's always a new line after a comment. The syntax for RT is fairly normal. It uses braces instead of indentation. Like most C-based languages, I've kept the global declaration from Python. I have two kinds of assignment. This equivalence says that this is kind of like a macro. The container is like a macro. It doesn't actually need to generate a temporary variable. It can be handled as a macro or can be handled as a temporary variable depending on the way you wish to compile it. We can make empty lists. We can make empty dictionaries. We can mutate fields, which means that this field has to either exist or be declared as a temporary variable like this up here. And we have macros for things that fall outside of the bounds of what can be handled by both languages at the same time. Append in Python is different than append in Common Lisp in this particular case. This is an easy breakout. There might be a way to come up with a syntax that's better than this, but I'm not doing that in this experiment. I'm just trying to see whether I can get somewhere with this. This operator is a lookup operator. It takes an expression on this side. In this case, the expression is a string, or in Lisp, that would be a symbol. We're looking for the ID mapped in a dictionary called child desk. When we find it, we take that value and temporarily assign it into a name we call ID. We have for loops, creating new instances of objects is done using the number fresh macro. I don't plan to go over the whole syntax of RT at this time, but we see the syntax pass here is really just a parse that raises syntax errors if the incoming text is wrong. The parse is written in OM.js syntax, and there's the whole syntax parser. And the rewrite just corresponds one for one with the rules of the grammar, and basically just does an identity transmission of whatever comes in, whatever tokens come in, go back out to the next pass, which is the semantic pass. Semantics checker is just more of the same. It's a parse of the internal form. There are places in the grammar where it was easier to write the grammar in certain ways that allow certain types of constructs that should not actually be allowed in the final language. The semantics checker should be a place where one would check for things like that. Here I've only done a little bit of checking. In particular, the def synonym rule breaks out two variants of the incoming text. And because this peg parsing, if it parses an identifier followed by the equivalent sign, followed by an expression, followed by more recursive statements, it calls a def synonym underscore legal. And if it parses anything else, an lval, or basically a more complicated expression on the left-hand side, then it's illegal. And if we look at the rewriter for that here, what we do is if it's legal, we just pass it on without much rewriting. And if it's illegal, then we jam an error message into the stream and say that the left-hand side must be a single identifier for def synonym. The build workflow checks for errors and stops the pipeline if there have been any errors encountered. Now we get to the more interesting part of all of this, where we actually emit Python. The transpiler from RT to Python begins with a generic shared grammar, which accepts the incoming internalized form after being parsed for syntax errors and for semantic errors. It comes in here. This is just another grammar. And in what we see here is that we break out all the different types of macros, I call them external phrases, allowed by this mini language. And again, this is PEG technology, so it tries them in order. So if it sees an octothorpe followed by the keyword low-level read text file handler, then it calls external phrase underscore read, and so on all the way down until the very end, where it says, I see an identifier with anything inside the parentheses, and I'm going to call it unrecognized, basically spitting out an error message that says, you've used a macro that isn't supported by this transpiler. Now we'll look at the emit python.rewrite file, which corresponds to the generic emit grammar. This rewrite file is specific to creating Python output. There's a different one for specific to creating Common Lisp output. And when we do future languages, there will be separate versions for those. This is just a basic rewrite. If we look at this, the interesting embellishment here is basically when we call def_obj with these parameters, the rewrite becomes this thing. This thing includes Unicode characters for indent and extent. And if you get these right, it produces legally indented Python. I use it for the Common Lisp stuff. You don't really need it for Common Lisp because it doesn't care about indentation, but indentation does help readability for myself during debugging. And what this basically says is, in this particular case, we want to rewrite the incoming trees as a new line followed by the word class, followed by the value of the ident here, this ident, put in here, followed by a colon, followed by an indent, followed by a new line, which will then get indented, followed by def, followed by a space, followed by underscore, underscore, init, underscore, underscore, parameters, self, comma, and then the interpolation of the formals that we got from a different rule, followed by a close parenthesis, followed by a colon, and so on. The line stuff here are the line number tokens that we generated in the internal form. They come out in the generated Python as number line comments. So in this particular case here, we rewrite the definition of the class component registry in this way, and it comes from line 4 of the RT spec. This stuff comes from lines 5 and 6, and then there's line 7, which is basically a new line. And then after generating Python, we feed the generated code into an exhaler. The exhaler decodes, removes the special internal characters. It indents the Python to be legal, and then it outputs it. The exhale Python pass itself breaks down into 3 parts: the decoder, an internalizer, and an indenter. The decoder itself breaks down into a call to a shell script. The shell script calls the transpiler using another shell script called NDSL. The transpiler takes a grammar, pydecode.om, and a rewrite file, pydecode.rewrite. I've got them here. They do very little. They just pattern match for things that I want to get rid of that are still stuck in the code. The most interesting one here is line. So when we see the magic characters for a line, we go down to the rewriter and we replace it with the Python comment number line with the numbers stuck into it. An internalizer is equally unimpressive. It does just a little bit of work. Basically, it reads whatever file comes in on stood in. It replaces double quotes and semicolons, and then does a decode URI, and there's some debugging stuff here. The final step is the Python indenter, just a little bit of code that tracks indents and outdent characters and does the right thing in a fairly brute force way to produce legally indented Python code, which then gets sent to the output. In this case, the output has no name. Finally, to tie everything together, I take the output from the pipeline, shove it through the choreographer, which is basically some Python code written by an LLM for me. And it performs a dance between a bunch of different processes. It allows me to draw the DPL program in draw.io, watches it, and triggers a recompile whenever there's a change here. The recompile calls a program called DOS2JSON to convert the draw.io file to a JSON file, and then runs some code not shown on this diagram called rebuild.bash, which generates the code. And then the final code is sent to the IDE. The IDE is called Programming Language Workbench.html, and it's really just a stock piece of HTML file that receives inputs. The choreographer uses several files. It uses a list of files to continuously check. And it uses a file that tells it which files to send with what tag to the IDE. The IDE looks for these tags and stuffs the output code into these boxes as appropriate. And as we can see, I'm prepared to do JavaScript, and if I knew something about WASM, I'd probably do something about that too.